Good afternoon, guys. So, welcome to the USVA BMI workshop series. So, today I'll be explaining about interpretability of deep learning models. Before we start, let me just give you an idea on why this is even relevant, right? Um, oops. Let me see. So, deep learning, especially in the current last 10 years or so, has been like the state of the art model in most of the classification problems. But there's a lot of advancement happening, and in pretty much most domains, the best model that we currently have might be deep learning models, but they have a big problem they currently face, which is a mystery black box problem. And what does that mean? Uh, these models might be able to give a good estimate that this is indeed a dog or a cat or whatever it's asked to predict, but we don't really understand what is happening inside the model. So it gives us a bit challenge because we don't know why the model arrived at this current output, right? Um, then the natural question comes like, why does it even matter? Should that even be a concern? Maybe not in situations where it's like choosing between dog or cat and things like that. That doesn't really have a consequence. Imagine a situation where you are in a clinic where unfortunately you have a condition and you are asked to do a surgery, and that surgery depends on this particular model. They say the doctor is currently unavailable. Now we have a model on in replacement for him, but we don't really know why it chooses the answers, but it's going to give you whether you need a surgery or not. Uh, that would be a very difficult position for someone to be in and to choose that particular option, right? Because we need to take informed decisions at that point. Now, this might seem a bit exaggerated, but indeed something like that is happening in the medical domain. The figure on the left here, this was a study that used a deep learning model to predict whether there is cancerous cell or not. And what they had a very good model that performed pretty well. The problem with this was uh, the data they said that he used was from the prior studies in the hospitals, and they usually followed this procedure where if they suspect that the image belongs to some cancer, they'll actually marking with a dye over here. Now, this might not be present in the in the images that is not cancerous. So there's a problem of data leakage. And when they explored the model a bit more, they found that the model was actually learning this dye and not the actual cell itself. Now, those are some instances where deploying these models might be a big challenge in the real world. So we need to build the trust in your model. Like, how do you arrive at this decision? That we need to understand. Which is why this particular workshop is aimed at interpreting your deep learning models, particularly convolutional neural networks. And before we go into the details, I'm going to have a poll just to know the audience here. If you guys can take a second and just mark your whichever is appropriate for you, that'll be great. Can you see the poll right now?
Yes, I can see it. How did you do that?
There's this option in Zoom for that.
Oh, that's awesome. Cool.
You did it through deep learning.
I'm sorry?
You use deep learning to do it, right?
So
That was a secret.
I'm pretty sure that was Alex. That's so bad.
Questions. You're not getting a deep learning of our like the demographics here.
Okay. I'm gonna give like 30 more seconds. Okay, so I'm gonna share the results. So we have a quite mixed range of people. A lot of them are undergrad or there's some high school students, but a lot of the people are new to the convolutional networks. So I'm going to tailor it such that I'll explain the basic concepts and then also give a bit of math behind all of this section as well. So we can try to answer both parties. Now, before I tell about the methods itself, let me give a background on CNN, because if you don't really understand the model that we are trying to interpret, it's going to be hard to make any sense out of it. Let's see. Okay, these are mainly the elements of a convolutional network, right? On the side, I actually mentioned what are the major ones. Convolution, you have convolution layers, activation function, pooling, classification. These are the four main elements of a CNN. Now let's go through one by one to have a basic understanding on them. Right. Now, how does the convolution work, right? To better understand that, think of yourself inside a black, dark room, right? Now you're stuck inside, someone put you inside that room and you have absolutely no idea what is inside the space. The only thing that you have is a torch. Now, how do you go about figuring out what is there? You basically light the torch around the room and try to make sense out of it, right? Now, think of the same analogy in terms of convolution. That's essentially what it's trying to do. Your CNN filter is like a torchlight. Now imagine this picture. You are lighting this torch, which is a CNN filter on the image. So whoever played around with the torch, you can see that there's only so much you can see with the torch depending on how close you are. So what you do is you scan the entire area, the wall or the actual image, and try to make sense out of what you see. When you talk about deep learning, we often tell about multiple layers, right? How does it manifest in terms of the torchlight? If you go farther and farther away, your beam actual circumference sort of increases. So similarly, the deeper you go, the receptive field or how far you see in the input also increases. So this is a basic idea on how the convolution would operate with an analogy. Now let's see in an actual image how that manifests. Now this is a video that shows how the convolution, hopefully this works. Oops. Well, that is not working. Okay, let's see. So in an image setting, how would that manifest, right? Think of this as the actual image, and this would be the convolution filter that you do. And this is similar to the, oh, now, okay, great. Give me 1 second. Right, so this is the image that you're trying to learn, and this is a filter, which is like the torch beam light. And assume that this is where the torch is, right, which is a CNN filter. Now, this filter scans the entire image and tries to find patterns from your data. Now, you have one of this representation from one filter. The same layer would have multiple sets of nodes, which is shown by here. Now, this node is going to learn a different feature from the data. Now, you repeat it multiple times. As you go behind, the number of layers increases. So as it progresses, you have a better concrete idea on what the data represents. Now, these are all good, but how does the computer see this, right? For the computer, these images are nothing but numbers. And when you say convolution filters, it's basically this box that you're trying to learn, and it extracts certain features. Now, when I say features, what does that actually mean in terms of image? In this example, this is one feature that the CNN actually learned. So it learned this filter corresponds to the edges in the image. So when you scan this filter across the image, it's going to give you a representation of the edges inside the actual image. So similarly, what your CNN tries to do is learn the filters to extract different features from your data. Now that is one of the elements which is called convolution layers in the CNN. The next thing you have is activation functions. Now, what are activation functions, right? Why is that relevant? A lot of the times the data inside in the real world setting, time series or image or whatever, they contains a lot of non-linearity present in the data. Now, if you just use a linear model, you won't be able to characterize these things. Similarly, if you want to increase the depth, you need a non-linearity present inside the data. Now, it can be as basic as this one called ReLU. Now, what does that ReLU mean? If I have an input that is less than 0, the value is less than 0, it wouldn't let it pass through. And if it is greater than 0, it would just let it pass through. It's as simple as that, but including that nonlinearity in your model significantly improves your performance. And that's another element of CNNs called activation function. The third element is called max pooling. Now, what does max pooling do? It finds the maximum value in an area that you're looking for. So for example, here it's 20 and the other one it's 30, right? It basically downsize the data. It also helps to improve the translation invariance. So if there's slight shift in the data between images, it sort of accounts for that. Now those are that's the reason why we use max pooling mainly. And the last and one of the another major element is called fully connected. And what fully connected essentially means is every node in one layer would be connected to every other node. So it's like, it's basically like this, right? It's also called densely connected. Now at the end, you'll have a fully connected network, which gives you a predictive probability for each of the classes. Now, in summary, this is combining all of these things that we end up getting a CNN model. You have an input, you feed it to multiple layers of CN convolution layers, pooling layers, and then activation function in between. You repeat that multiple times depending on the depth. And at the end, you have some fully connected network. And then at the end, you predict whether the image is actually a car or a truck or whatever your classification problems are. So that's a bit background on what CNN are. Give me 1 second. I have a question. So there's a question by Chris. back to the flashlight analogy, would you say more layers equals better always? So there is no always question, in especially it comes to deep learning, because a lot of the times it depends on the data and the number of examples you have. Sometimes your data might not be as complex so that you need too many layers. And sometimes if you do too many layers, you might be overfitting the data. So it really depends on your data set that you're working with. And there is also something about the total area that the filters can actually see. So it is not, there's no always question. For example, in EEG, what we found is a shallower network with less number of layers are typically found to be better. But at the same time, in terms of images, we have layers which are like hundreds and 200s of layers. So it's specific to domain and the actual application. Thanks, Chris.
Great. Thank you.
Another question, can you have a semi-connected network and a fully connected one? Actually, yes, in some sense, yes. So one of the ways you, I don't want to say semi-connected. So one of the ways people avoid overfitting is called dropout. In some sense, what they do is in certain iterations while training, they drop the connections between the layers. So in some sense, at that point, it's a semi-connected because it is losing some connections, and so that it doesn't overfit to particular channels or data points specifically. And there are other people who also try to do, they constrain the connections so that they sort of have controllability on that. So yes, but it's not very often used in general. But yeah, thanks, Chris. Thanks, Alex. Let's go forward. Another term that you need to be familiar with is gradient descent when you talk about deep learning. Now, why is gradient descent even used, right? Just understand that gradient descent
Akshay,
is
are you there?
yeah. Who's that? Do you have a question? Can you see the slides now?
Yep.
I
You're
hope
good.
did you guys lose me at this slide or from the start of the presentation? Okay, let's see. Right, the another
Back slide or two.
Stuck on the pooling on the architecture.
Oh, okay. Here. Okay. Let's start from here. So oops, here.
Yeah.
Yes.
Okay, so this basically summarize, right? The elements, how does it manifest, right? You have an input, then you have multiple layers of convolution, max pooling, and activation layers. And at the end, you have a fully connected layer, and you have a predictive class at the end, which says whether your input is a car or something. So that's essentially how the CNN would manifest in. Something else you need to understand is gradient descent that you might come across a lot. What does gradient descent do, right? It is just a way for you to understand what are the best model weights. So it's a technique to estimate that. Now I'm going to try to explain that with the basic example that everyone is familiar with, just a line, plotting a line, right? If you have a data like this, the model for this is having a line to fit the entire pattern. And it's called y equal mx plus c, which we are all familiar with. Now, what does gradient descent do? It tries to minimize the cost or loss function. Now, what is a cost or loss function here? It is in some sense to quantify how much modeling error is present in your data. So for different combinations of your model, you'll have a predicted value and the actual value. Now, the error between that is typically explained by a cost function, and gradient descent is trying to minimize for what value of W and B can I have the least error in my model. Now, take the image on the left. These are just the loss function, how it changes for different combinations of W and B. So for this particular value of W and this particular value of B, this would be my loss function. That's essentially what is shown in this figure. Now, in terms of neural networks or CNN training, we use gradient descent. And let's say initially you start with the random weights, W and B, at this point here. And what do? We compute the gradient at that point, which is essentially the direction of the steepest descent, and find which direction I need to move, update my weights, so that at the end I reach this point, which has the least value of the loss, right? Now, we basically move this in different directions until we converge to the point of least loss. Now, this is in explaining in terms of just two parameters, W and B, which is basically two parameters, right? Now you basically expand this to thousands of parameters. Essentially, that is what, but the method is still the same. That's how the CNN is generally trained. So when I talk about gradient descent or ascent, this is essentially what we're talking about. Now that's a background on the actual network and stuff. Next, let us give a brief overview on the different deep learning frameworks we have. These are the commonly used ones right now: Keras, TensorFlow, and PyTorch. These are some comparisons I made, and I would summarize that if you have a very rather smaller data set, and if you are just starting out, Keras pretty much is the best method out there, best framework out there. But at the same time, if you have GBs and terabytes of data, Keras might not be the most appropriate toolbox. Then that's when TensorFlow comes into play. It's more complex. It has both high level and low level API, and it offers more flexibility. Now, PyTorch, on the other hand, is more complex, but it has better debugging options, but it's a bit complex too, right? In general, most applications I've noticed that these are sort of an overkill because most of these can be done here. So depending on your expertise and stuff, you can do either. Now, for this tutorial, we'll be focusing on Keras because I believe most of them are new to the session as well. Now, a few pitfalls and stuff that is very essential when you're working with deep learning is cross-validation. We need to revisit it. We do typically call them by training set, validation set, and test set, right? And how we prepare the data in general working with EEG is you have a window, which is like the shaded portion here, and you basically shift it by a few samples. So there's an overlap between one window with the next, and there's an overlap with the one window with the next one, right? Now, sometimes what people do is they window it with overlap for the entire section, and then they shuffle the entire data set into tuning and testing set. Now, that is a very bad way of going about doing this. The reason for that is, even if I have this window and this window in training set and the next window in the testing set, this much portion of the data is still common in both sets. And if I have another set parallel on the other side, so essentially the network is going to see most of your data in the test set as was already seen in the training set. So that's a very bad way of going about doing it. So first thing you need to do is, I think someone's mic is on. Can you guys try to turn it off? Okay. So the first step we should try to do is separate them into training set and testing set and tuning set. I intentionally renamed it to tuning set instead of validation set. This is something I saw in the latest post because essentially in deep learning, the validation set is used to optimize your hyperparameters. So it's better to call it that because test set is going to be very separate. You cannot show this at any point to the deep learning model. And when you do cross validation, it should be between, you just shift this tuning set at different time points. And this is the source from which I learned this. These are a different way of renaming the training, validation, and test set. Instead of test set, it's better to be called reporting test because that's the accuracy that is most valuable when you talk about performance scores. A tuning set is mainly for hyperparameter optimization. Now that's a bit of background on the actual CNN and the things that you need to understand for this tutorial. Now let's go to the actual method itself. Now I'm going to try to walk you guys through how the human sort of perceives, and I'm going to relate it to how a CNN would actually be looking at the same thing. And I'm going to use this, I think everyone would have been familiar with this illusion, Deco rabbit illusion. This particular method is called occlusion sensitivity. Now, depending on how you look at this image, it could be either a duck or a rabbit. Similarly, this could be a young lady or an older woman. So what happens is, if I occlude a certain region in the image, like I hide a certain part of the image, then there's a good chance that you classify this to be a rabbit more than the duck right now. And similarly, I'll be more inclined to classify this to be an older woman than the actual younger woman. And what if I occlude another part, right? If I occlude this part, there's a good chance that I'll be classifying this to be a duck instead of, and this to be a younger lady. So there are certain parts of the image, depending on where you focus your attention on, we tend to arrive at this conclusion. The same thing applies for these machine learning models. Now, if I have a model that is built to classify different classes, I have a portion of the image which I occlusion section which I pass across the entire image and see how my prediction score changes depending on the movement. So if this occlusion part is around the face of this Pomeranian dog, the prediction power drops significantly. That shows that the model actually learned to focus on the face of the dog to arrive at that conclusion. Similarly, in here, if I occlude the area around the tire, that's when the actual classification score significantly affects. Now, we'll be using this method, this intuitive idea on try to see if the model actually learned the data representation we have. Now, that's method number one. And this is not specific to deep learning. This can be applied to any model, as a matter of fact. The next one method we'll be going across is called activation maximization. To explain that, let's try to go through the monkey behavioral experiments, right? In behavioral studies involving monkeys, when they have a new monkey inside the lab, it wouldn't really know what it's supposed to be doing. It's going to do random actions. And at times when it does correctly what it's intended to be doing, they get a reward. They get a fruit juice or something. So after a while, monkey sort of does random things, and then it understands what are the things I need to do to maximize my reward, right? And then it keeps on doing the correct action so that it always gets a reward. Now think of the same thing in terms of the CNN, and this method is going to be similar to the monkey analogy. We start with a very random image. Now the image can be considered as the monkey's brain state, so it doesn't know what it's supposed to be doing. It's very random. Then I tweak my input in such a way that I increase my chance of making the correct prediction for the class. So if I tweak it in some direction, I get a reward. Essentially, that is a prediction score of my class. Now I keep on moving my input multiple times until I maximize my reward. So that is essentially what we are doing with this method. You start with a random input, which is a random squiggles. You feed it to a pre-trained model. You get an activation score. Now you tweak your input in such a way that it increases the max activation score for that particular class of interest. Now you keep on doing this. This is called gradient ascent. You do the opposite of minimization. You're doing the maximization. You maximize your score by perturbing your input until you get a input that maximizes the activation score for that particular class. Now, once you get that input, you compute the power spectral density and then check whether the actual Ph.D. Relationship between the classes is retained in your model. That is another way we'll be performing this method. The third method is called grad class activation map. Now, to explain this, another background, right? I mentioned about the receptive field, right? As the number of layers go, the units there will have a larger observation field of your actual data. And again, to explain this, let's go through. I'm going to make you guys be a CNN and how we'll be perceiving this for the time being. I want you guys to focus on these letters and try to see when it makes sense to you. Right. So towards the end, I think most of us will be able to make a sense of what this means. It's a human mind, right? But in case, what if I followed in individual letters? If I was focusing on individual letters, this doesn't make sense. MUAN, that doesn't make sense, right? Similarly, when you have a CNN, the initial layers, like the initial layers that you have, might just be very abstract, very basic features, like it might be edges and stuff. Now, as the number of layers increase, you have better abstract representation of your data. For example, in faces, you have a good representation of what the face would actually be entailing. Even in here, even though these are incongruent in some sense, but you do get an idea when you have when you look at it from the entirety. Now, why do we understand this thing, right? According to a research at Cambridge University, what they found is if you keep the first and the last letter intact and you scribble everything else in between, you will still make sense of the actual word itself. Now, how did they come to this arrive at this conclusion, right? If they have to make this inference, they need to see the entire word and then see which part of this word the people were mostly attentive to. So, if, for example, they found that looking at the first and the last word, that's when people will perceive it, right? So, in order to understand that, we need to arrive at this question. Essentially, that's what GradCam is doing. You have an input, you feed it to a CNN layer. The last convolution layer would have the most richest representation of your data. Then what you do is, this is a predictive score that this image has a tiger cat. So in this picture, there's a dog and a cat. Now, where should I look inside the image such that I should classify this to be a tiger cat? Now, how do we arrive at this is, you compute the gradient of the score for this tiger cat. with respect to the activation of this particular, the last convolution layer. Now, what would that actually give, right? Think of it like a weight that you assign to these filters um, to make the correct conclusion that this belongs to a diagram. So how much does each of those filters contribute to arriving at the correct classification score? So that is essentially what the W1, in this case, it's alpha K. That's essentially what it is doing. And when you multiply your weight with the actual heat map of heat map is nothing but how the image is perceived by each of those layers. And you sum them up all together, you get the class activation map. And you will be passing it through a nonlinearity ReLU because you only want to add up those things that positively contribute to your predictive score. Now, essentially, that's what we are doing. We get a class activation map at the end, which highlights a region which is most contributing to the prediction, and then we upsample it to your image itself. Now, these are the three methods that we'll be covering, and I'm going to go through the Google Colab right now. Before that, if you guys have any questions on it until now, just let me know before we go there. I guess you guys can see my screen now, right? Okay.
You're good.
Okay. So I'm sharing a copy of it. I want you guys to sort of copy this to your drive. There's going to be an option called copy to drive. Click that. And did you guys were able to copy the files to the Dropbox? I mean, your Google Drive? Is everyone able to do that? Because if you're going to try it right now, you'll need the files inside your drive. So I'm gonna go through this code one by one, by cell. So what Google Colab does is it allows you to run the Python or whatever code you have on the Google Cloud. It provides you with the GPU and stuff. So this particular tutorial is aimed at implementing the three methods that we mentioned, and we are going to learn how to train a model in Keras, and then it's going to create the model using that, and we are going to see how the three methods can be implemented. And we are going to be using the same data set that we've been using, the eyes closed, eyes open data, which has 10 repetitions of eyes closed and eyes open. There are some notes which I would like you guys to go over afterwards. Now, in general, how this works is you need to, if you have some libraries and things you want to install in Google Colab, you need to predefine it. So right now, I've already, let me see. I've already run this before because it might take some time. So you guys can go ahead and click one by one. If you click the run cell over there, it's going to run that particular cell. I've already run it so that there's no delay and stuff. So the first thing you do is I install all the packages and libraries that is needed. The current package I'm using requires a older version of TensorFlow and Keras, so I'm downgrading it to another version. You need to give access to your Google Drive. Actually, you know what? Let me go through the first steps. Oops. Yeah, maybe just run it one because I don't want to rerun it. So if you run this once, it's going to ask you permission to access, give access to the Google Drive. Click that, and there's going to be a link that is going to pop up. Copy that inside here, and that's going to give you access so that the code can take data from your Google Drive. Now, once all of this is set up, you need to import the libraries to this particular lab. So these are the functions that you need. Some of them are general functions, some of them are specific to Keras, some of them are for visualizing purpose. So once you run this, what you need to do is load the actual data, right? So this section, this particular part is for loading the data. Now, before we try implementing that, let's get a sense of what the data actually looks like and what are we dealing with. So this contains 10 trials of eyes closed and eyes open, and each of the trials are 10 seconds long. Now, beforehand, I've already segmented into training and tuning set. For the sake of this purpose, I'm not testing. I'm not having a testing set because I'm not intended to report the scores. I'm more like just because it's very small in length, and just want to show how it's working. So we've randomly selected trials such that prior from tuning set and training set. And let's also try to visualize some of the examples. Let's try to visualize some of the examples. These are just two examples of time series of each classes, eyes open and eyes closed. And we've also, the next step actually plots the mean power spectral density and the top of plot distribution in the alpha power. So you can see there's a big peak in the alpha, and these are mainly localized in the occipital parietal regions. So because if this is the pattern that we are trying to learn, our CNN should be able to know that there's an alpha peak, and that's the most discriminating feature, and it should also know that these are the most relevant channels. So at the end, your CNN should be able to learn these two features. And before you do any classification, always have a sense of your data. Okay, and the next step we are going to be doing is preparing the data for training. Once you saw the data, you know how the data is supposed to be doing, supposed to be looking, then we need to prepare it such that the Keras library can read it. So this steps involve mainly normalizing your data, shuffling your data, etc. Once that is run, there are some hyperparameters that Keras needs. So a lot of the things might be going over your head right now, because if you're not familiar with this particular library, some of the things might not be comfortable for you, but that's fine. Come back to the script later on. What I'm trying to do with this session is I'm introducing you to different cells so that you understand what each cells are doing. If you don't understand any particular part in it, go back and try exploring that at your own pace. I've commented all the lines as much as possible to help you out with the code. Now in here, we've initialized all the hyperparameters for the model. And now I'm going to actually implement this neural networks, right? So this particular layer network has 7 convolution layers, 3 max pooling layers, 1 dropout, 1 flattened layer, and 1 fully connected layer. Now, once I define this model, I'm actually going to, this is a summary of the model. It has almost 100K parameters. And then I train the model. This line is used to train the model. And when I run it, it's going to show me how the validation score basically and losses changes. And once the training is done, I do some model evaluations. Essentially, we wanted to see how well the model is performing on the validation set. And I'm computing some performance scores here. And I'm also plotting how the training actually went. Now, this is very important when you're training a model, because if you see here, this is a training loss and the validation loss, how it improves over the period of time. Sometimes what happens is, even though the validation loss is increasing, even though the training loss is increasing, the validation loss might actually be increasing. Like it might take a U shape. Now that suggests that your model is overfitting to your training set. So it is learning just your training set, and it's not really generalizing properly well. So always when you train a model, try to check these things to see whether it is indeed overfitting or not. Right now, I have something called early stop condition. So if it starts becoming overfitting, I'll stop training at that point. So this section, until this point, we've trained the model. The model is now currently trained. Now let's actually try the methods that we mentioned, right? The occlusion method. What we do is, for the sake of this workshop, I'm only occluding per channels, 1 channel at a time, and see which is the most relevant channels. So we copy the data and I occlude one of those channels by making them 0, because it's centered around -1 and 1. And then when we plot and see how the performance decreased with respect to the actual model, you can see the channels. If I occlude the channels in the occipital parietal region, this is when the model significantly gets impaired, or the performance significantly drops. Now, this is the same trend we saw in the actual data representation. So we know that the model is indeed looking at the most relevant channels right now. That's one way to look at it. So as I mentioned before, this is not specific to deep learning. You can do it with any model, any linear model or whatever. The next method, however, is specific to the CNN architecture and the model that you're trying to do. Here, we do the activation maximization, which is trying to find the input that maximizes your score for a particular class. And once I run this, you need to check the scores here over the period of time, if it is decreasing or not. So this has to be decreasing. If not, you're not doing it correctly. So you need to change some parameters here. These are some regularization. Try to play around with that. Ensure that this is dropping continuously. And once that is done, what I do is I compute the power spectral density of the generated input. So we know for sure that the input actually has the alpha power. So if you see here, these are the 2 power spectral density of the maximized input. And what it tries to find is, it does find that the highest peak is in the alpha, and that is in the ice close condition. So that representation is captured by the model, and it is still prioritizing channels in the back of the head. So the model is learning these features when you're training it on the data. that's another way you can explain that the model is indeed learning the actual data representation. Now, the third method is the GradCam. And here, what we essentially identify the models that it correctly predicted to be correct. That's what we're doing here. We select the examples that the model said it is correct. And then we compute the GradCam as I explained before on the last convolution layer. And what we find is even using that, we do identify that the distribution is in the parietal occipital region, and that's it's learning the most relevant channels even in this case. Now, a lot of this, what I mentioned, is mainly based on the topological distribution. Now, how does the GradCam works when you have an actual time series data? And to do that, I fed another data where half of it is from eyes closed and half of it is from eyes open. Because until now the model was trained on just eyes open or eyes closed, right? Now what happens if I feed a data that has both eyes closed and eyes open? So the first part is eyes closed and the second part is eyes open. Now once I run it, I can see that it is focusing on the eyes closed region, and it is learning that it is during the alpha band it's high and it's not much activated in the lower channels. So it is indeed learning these representations both temporally as well as the topographically. Now, these are a few methods that you can do to check that your model is indeed working the way it's supposed to be. Now, if you guys want, you guys can go ahead and try each of them on your own pace. But that's pretty much it for the session for today.